Good morning. Let us start discuss about the Thevenin's theorem. Thevenin theorem states that in any linear bilateral active network containing more than one source, one or more sources can be replaced with an equivalent circuit consisting of a voltage source in series with a resistor. The voltage source being the Thevenin's equivalent voltage and the resistance is the Thevenin's equivalent resistance. So let us consider two networks, network 1 and network 2 across A and B. Now what we are going to do here is that we are trying to replace the network 1 and network 2 with their Thevenin's equivalent circuits. So how to do it? Let us move on. So remove the network 1 from A and B, and it might be a complicated network consisting of so many sources and resistors. So first what we need to do is remove the load or the network connected across A and B and find the voltage across A and B, which is the open circuit voltage across terminal A and B, and it is equivalent to Thevenin's voltage. Now deactivate all the sources of network 1 and the resultant will be a simple resistive network, which we can find out the equivalent resistance across the terminal A and B. Let us take an example of the following circuit, which consists of 3 voltage sources, 2 current sources. The voltage sources are replaced with a short circuit and current sources are being replaced with the open circuit. That is, we are considering the voltage sources as ideal independent voltage sources, and if we replace the current source by open circuit, it is as good as replacing it with its internal impedance, that is high infinity, and the voltage source, ideal voltage source internal impedance is 0, that is by short circuit. So how it will look like once we do that is this. Now it's a simple resistive network. You can find out with the series parallel combination of R, you can find out the Thevenin's equivalent resistance. Once we are done with it, we can find out the Thevenin's equivalent resistance across A and B and connect it back to the network 2. So repeat the same, we can repeat the same procedure for the network 2 and connect it back and calculate the current flow out of network 1 and current flow out of network 2. We can find out and use it for our analysis purpose. So let us find out the let us find out the Thevenin's equivalent network across A and B in the given example. So here 30 volt source is taken and a 2 ohm resistor is taken as a load, that is across terminal of interest is A and B. Now first what we need to do is we need to remove the load resistance, or the, in our previous example it is network 2. So once we do that, we are going to find out the open circuit voltage source voltage, that is across A and B, which is a simple, it is shown VAB is equal to 30 into 6 divided by 6 plus 12. How it is? It is the voltage across the 6 ohm resistor, since 4 ohm becomes a redundant resistor. To find out the Thevenin's equivalent resistance, voltage source is being replaced with the short circuit. So the Thevenin's resistance is, equivalent resistance is 8 ohm. So now we can replace the network with the Thevenin's equivalent network, and we can easily find out what is the voltage across the A and B when we connect the load. So sometimes we need to we can't able to find out the equivalent resistance where the network consisting of star and delta resistors are connected in star and delta fashion. It is easy to find out the short circuit current in the network rather than finding out the Thevenin's equivalent resistance. Once we find out the short circuit current, we can easily find out the Thevenin's equivalent resistance and replace in the network. Thank you.